All right, guys. So what I wanted to do is kind of go over deriving the conservation of energy, starting with Newton's law. A lot of times you are in physics class and you cover Newton's laws, and maybe that goes okay. But then you get into this weird stuff of potential energy and kinetic energy, and sometimes it doesn't really make sense of where it comes from. Just kind of is something you're just given. And the history of how it was come up with, kinetic energy and potential energy, how those ideas were come up with, is interesting. But it's also pretty fascinating that we can start with just Newton's law and get conservation of energy from that. So I wanted to show how that happens. So we're going to start with Newton's law. And we're going to start with I know there's multiple Newton's laws, so you might be wondering, which one's? The one we're going to start with is F equals ma. And of course, those need to be vectors. I always indicate my vectors with a little underline. This will be F equals ma. And we're going to go from here, and we're going to go to energy conservation. And so kind of, how do we do that? And it's really not too complicated. It might seem like it would be a pretty crazy thing that we would have to do, because obviously energy conservation looks totally different. And let's just kind of remind ourselves of what we mean when we say energy conservation. What we mean is when we have a system, something, right? Later we're going to define one where we have like this box and it's moving. When we have something and it's over here doing stuff, it's moving at some speed or whatever, and then later it's over here moving at maybe a different speed, we say that the amount of energy that it had here has to be equal to the amount of energy it has here. So that the final energy has to be equal to that initial energy. And that's all we mean by conservation of energy. And so we would write that down by saying that the initial potential energy plus the initial kinetic energy has to be equal to the final potential energy plus the final kinetic energy. So that's how I'm going to notate these. This is the potential energy. Oh man, there go my heaters. Don't know if you guys can hear that. Okay, so this is potential, and then the K is kinetic. So that's what we're talking about. Okay. So I'm going to do it 3 different ways, depending on where you are. Everyone takes physics classes with different amounts of math, and you may have a different amount of math that you're comfortable with. So we're going to do it in 3 different ways. We're going to do the first one here with algebra only. Although we will require some vectors as well. We're going to use vectors on all of them because really, if you're not doing physics with vectors, you're making it really harder, right? Really harder. You're making it much more complicated and much more difficult to understand what's happening. The vectors, although sometimes it can seem like they're making it more difficult, it really does simplify things a little bit. So the second way is going to be a little bit of calculus. So that will be we'll say through Calc 1. Through Calc 1, and a little bit of calculus. It kind of depends when you cover integration. So plus a little bit of integration. So plus some integrals. And I have to require a little bit of integrals. Otherwise, we won't be able to get the result that we need. And it kind of depends, if you cover some integrals in Calc 1, some schools don't. It really kind of depends on what your experience was with that. The third way is going to be through Calc 3. I feel like once you've done 1, 2, and 3, it's pretty universal in terms of this kind of stuff that you've seen. So we'll say this last one here is going to be through Calc 3. So those are the three methods. You know, if you're looking to get to see number 3 here through Calc 3, I would recommend that you watch the first two ways, because there might be something interesting there that you find out by doing that. But by all means, you know, if you're only doing physics with algebra and you have no idea how to do any calculus, just stop after number 1 there, because then the rest of it's going to be stuff that you won't really understand. With that said, we'll move on to what the picture is that we want to be doing. So we have to define what our system is, and it's going to be the exact same system for all three explanations. So we're just going to draw it once, and then move on from there to the three different things. So we're going to define an initial situation. So we have some initial situation here where we have some ground. So here's the ground. Okay, that's just the floor, whatever. And then we have a box. And the box is right there. The box has a mass, little m, that's how much it weighs. We have the box is located at some height, like that, above the ground. And I'm writing a little lowercase I there on the height to indicate that this is the height, h, for that initial situation. So this h, little I, is that height for this picture. And the reason I'm doing that is because I'm going to use h again for the final situation once we draw that. The box is also moving up at a velocity vi. So remember that velocity is a vector, so it gets a little underlined. Also, I've drawn it off to the side a little bit. Just, you know, let's just, know what it is that we mean. That's the box moving up. I just don't want to clutter up the top of the box because I'm about to draw a force on the box. And at least for me, I think forces should be drawn on the thing that's experiencing them. And it gets confusing if I do the velocity on there too. So the box is experiencing a force, which is a vector. This force Fp, the P stands for pushing. So you might imagine that's like, we're like pushing the box up with that force. So that's us pushing on the box, lifting it up, okay? And then of course there's gravity around. There's gravity hanging out here. So gravity is going to be, oops, that gravity, what did I hit on the paper? Little bump on the paper there. Yeah. Little bump on the paper. Okay. So gravity is a vector pointing down, which means the box, since it has a mass, is experiencing a force due to gravity pointing down. So that little g there on that F is just signifying that's the force due to gravity. This is the force due to push. Okay, then we have a final situation, okay, where the box has moved up. I should say this is the final situation. Okay. Can I make my head tinier here? Yeah, let's make my head a little bit smaller. There we go. Okay, so the final situation, we still have a mass of m. We haven't lost or gained any of that, which is good. We are still experiencing a force Fp and a gravity Fg. The height of the box is now hf. It's changed. And in this depiction, it's increased, right? The height of the box is moved up. So in this depiction, it's increased. And the velocity of the box is vf. So the velocity's perhaps changed as well, going from this initial situation to this last picture here, this final situation. Let's have a look at drawing a line here all the way across so that we can see how high up the box is moved, because we're going to need the displacement, right? If you remember when you first started talking about energy, you might have talked about work, and work is the force times the displacement, not just the position, but how much it's moved. So we're going to need that displacement. And so what we're going to do here is we're going to say this vector here that starts right there at that position, that starts at this initial location, goes up to the final location. This is our displacement in the final situation. We also need to make sure that we define a coordinate. So we're going to have x be our coordinate and plus is going up. It's always arbitrary. I always tell people it's up to you. You could pick diagonal, you could pick down, you could pick whatever you want. Easiest in this case, everything's moving up and down. Just go ahead and pick up. And we're going to go ahead and pick up as being plus. We'll go ahead and define what we mean by this displacement vector as well, just so that it's absolutely clear. What we mean is that the displacement vector, notice there's no f or I there, is equal to the height minus the initial height. And this is then going to be in the x direction. So this here is just a unit vector that points in the x direction. Sometimes classes and textbooks will use I, like a lowercase I for that with a little hat over it. This is just the unit vector pointing in the x direction. So notice that this doesn't have a subscript on it either. That's because this could be any height. Once we make it the final height by drawing a little f there, this then becomes the final displacement. If we had it be another I, because we wanted to know what is that initial displacement, the displacement over here, well, obviously this would be hi minus hi, which would be 0. So that initial displacement would be 0. So that's what's going on with that. The initial displacement, 0, final displacement, non-zero, and that's how much it is. So like I said, this is going to be our final, our initial and our final situations for all three explanations. So let's go ahead and get started on algebra only then. So I'm going to trust that you've drawn this out so that you have a copy to look at for that. Get my paper on the camera here. It looks a bit blurry. Let's bring this back. Hit this button. Perfect. Okay. So algebra only, let's do that. There are a few things when you're doing algebra only. There's some things that are assumptions or requirements for that. So one thing is that everything has to be on a single axis. We could do it on multiple axes, but that's going to make it more complicated to look at. So we'll go ahead and stick with one axis. We're going to definitely want constant acceleration. So we're going to want constant acceleration, which means we're going to need constant net force on our box. And in this case, we're going to assume that our pushing force, we'll look at the initial picture, that our pushing force is greater than our gravitational force, which means that the net force is going to be pointing up, so the box is going to be moving up, like how we've drawn here. And that means that the acceleration is going to be up as well. So we're going to assume that the magnitude of Fp is greater than the magnitude of Fg. And so that therefore our acceleration vector points upward. We also have to be very, very careful with plus and minus signs. I don't know what it is. Maybe it's a personal problem of me, but I always seem to be struggling a lot with figuring out what to do with these plus and minus signs when we make a lot of assumptions here. So I like to say extreme caution with plus minus signs. So we'll just have to make sure we're careful. It will work out okay for us here, but I will say if you try to have the acceleration go down, it gets a lot more complicated, just because then you have to be really careful with the signs. So I don't think we'll have to exercise too much extremity in our caution, but we will have to be a little bit mindful of what it is that we're doing with that. Okay, so the force, like I said, we're going to start with F equals ma. And when we do F equals ma, remember that the F of it is that net force. That's equal to the mass of the object times the acceleration of the object. Now we know that work, like I said, is F times the force times displacement, but it's not just times, right? It's a special times, right? It's work is, if you remember what that is, work is force dot product, right? So that's what the work is. And remember that this can also be written as the magnitude of those vectors times the cosine of the angle between them. So this has to be the angle between them. Okay. So that means in this case, right? That means in this case, since our displacement is going up, and let's say FP also going up, let's see, that one's going up like that with that pencil. This one's going up like this. Those are parallel to each other, right? So the angle between them, if we bring them together, right, kind of stay there, pencil. If we kind of bring them together, there is no angle between them. The angle's 0. The cosine of 0 is 1. So Fp dot d, the displacement vector, is just F times d, just the magnitudes multiplied by each other. Fg, on the other hand, since it points down, its angle is 180 degrees, right? So you have to flip the pencil all the way, and it's 180 degrees away in order to get to where it's pointing. Cosine of 180 degrees, or cosine of pi, is -1. And so the product there is negative of the magnitudes multiplied by each other. So that's something we're going to have to be aware of, is that definition of that there. Let's get to that situation, though. Let's break up our F net and have this be Fp plus force of gravity equals ma. And now we want to apply work, okay? So that way it's energy. We're just going to make all of it some kind of work. Remember that obviously both of these are forces. This is also a force. M times A is also a force. It must be a force because it's equal to these things, which are forces, okay? So once we multiply this thing by displacement vector, it's all energy now, it's all work. Then it's just doing a little bit of effort and manipulation of the equation to make it look like conservation of energy. So then all we do is we say that this is going to be Fp, and it's going to be multiplying all the terms by d, right? You can't just multiply one of them, has to be all of them. So it would be Fp dot d plus Fg dot d equals ma dot So now what we want to do is we kind of want to take a look at each one of these terms individually. This one, then this one. So let's have a look at this first one. We kind of already discussed it a little bit. We'll say fp dot d. Now we already discussed this one a little bit. Fp points up. The displacement vector goes up as well. That means they're exactly parallel to each other. So therefore the cosine, sorry about that, I completely lost myself. Therefore the cosine of the angle between them is 1. Okay, so that means this is just equal to fp times d, which hopefully you'll let me get away with not having to write the little vertical bars. It gets really messy after a while trying to look at all of those all the time. Let's see, I'm gonna cut real quick. Okay, and I'm back. Sorry, I just thought there was something weird going on with the audio. Okay. Okay, let's see, where were we here? Right, so we have the fp.d is just fp times d. And that's because they're in the same direction. Now, let's do this term. Fg, force of gravity, dot d, equal to. Remember that the force of gravity is just m times g, right? So that's going to be m g dot d. And now g and d, remember the d vector, displacement points up because our box is moving up, but g points down, so it's in the opposite direction, and so that gets a negative sign. So that's going to be minus mg d. Opposite direction. Okay. There go the heater again. There's no way you don't hear that, right? All right. So, we've got this last term then. ma dot d. Well, of course, a is pointing up because we said that that's what we're going to do. So a is pointing up, and d also points up, so they're in the same direction again. So we have m, a, d, mad. So let's substitute those three results in to this equation here. And we get fpd plus, oops, I already messed it up, minus mgd, and then equals this, equals mad. Now, what we would really like to do, this is fine, but it doesn't really look much like energy conservation. What we would really like to do here is get, instead of D and instead of A, we would really like to have things in terms of variables that appear in our picture. We would like it to be in terms of V for velocity and H for location, for how high up the box is. That's what we would like to do. So let's make our way towards doing that. First of all, what is D? We know that D is, not as a vector now, is the, so what's the magnitude of it, right? The magnitude of it is going to be that final position minus the initial position. Okay, it's going to be the magnitude of it. But what is this a times d? What is that? The acceleration times distance. What is that? So what do we do for this guy here? What do we do for that? And this is actually a really cool part. What we do for this is, remember, we have to assume that there's constant acceleration because we're not using calculus. If we're only using algebra, acceleration has to be constant. And if we have constant acceleration, that means that the acceleration is equal to the final velocity minus the initial velocity divided by the final time minus the initial time. What I mean by final and initial time is, sorry, I think I'm gonna sneeze. I think I'm okay. I feel it's gonna come though. What we mean by final and initial time is we have some amount of time here, maybe it's 1:05 p.m. or something here, and maybe it's like 11:30 a.m. over here, right? So that would be the final and initial time. So however much time passes going from initial to final is what we find by doing final time minus initial time. That just gives us how much time has passed. That's all we mean by that. But yeah, remember, this is only for constant acceleration. Only for constant acceleration. You might recognize this as also being how we could define the slope of a straight line. Slope of a straight line has constant slope, constant acceleration, and that's not a crazy coincidence. That's intentional. Okay. Right, then what we can do is we can say that a times d. We just substitute this in for a. Vf minus Vi over Tf minus Ti times d, but remember d is Hf minus Hi, so Hf minus Hi, and then we can write this as Vf minus Vi. If we just slide this t, this difference in time, slide that over to being dividing the h's instead, we get this. What this gets us, you might recognize that as the average velocity. So this thing here is the average velocity. Okay. What we can also say is that as long as we have constant acceleration, again, have to have the constant acceleration, as long as we have that, then we know that the average velocity is equal to the final velocity. Then it's equal to literally the average of the velocities. The final velocity plus the initial velocity divided by 2, right? That's kind of how you would average something. Then the average velocity is just equal to this. So this gets us the average velocity for sure. Acceleration doesn't need to be constant. This gets us the average velocity only for constant acceleration, right? This one, acceleration can be anything, and that's just how you would define average velocity. This is only for constant acceleration. But since we have constant acceleration, that means these two things have to be equal to each other. So we can substitute this expression in for average velocity over here. One half. There we go. Now let's just simplify this. Let's multiply these things through, huh? Let's do that. So we'll have 1/2. VF times VF will be VF squared. VF times VI will be plus, because we have two pluses, plus VF times VI. Negative VI times VF will be minus VI times VF. Negative VI times positive VI will be minus VI squared. These two terms here are the same, so they cancel out. And we end up with 1/2 VF squared minus VI squared. And that is a D. And so hopefully, yes, hopefully you're recognizing that this kind of looks like kinetic energy, right? We at least have a little velocity squared in there. So that's kind of fun, right? Yeah, I think so. Okay, so let's substitute in this guy here, this AD situation. Let's substitute that in. Let's also substitute in what this D is here, this HF minus HI. So let's do that. So we get FP times D minus mg, HF minus HI equals, gonna have to write on a second line here, I think, 1/2 from that 1/2, and then the m here, and then AD, the rest of AD is the difference of the squared velocities, VF squared minus VI squared, and I got it in there. Okay. So this thing is just final kinetic energy minus initial kinetic energy, right? Well, sure. This is KF minus KI. What about this thing? Let's have a look at that. So this is FP times D minus mg HF plus, just distributing this mg, HI equals KF minus KI. This mgh, potential energy, right? This is final potential energy. So that means we have FPD minus final potential energy plus initial potential energy equals KF minus KI. Let's move the finals and the initials to the same side of the equal sign here. Or what we can do instead, let's leave the FP times D on the left-hand side, move everybody over to the right-hand side. FPD stays on the left-hand side, equals the final potential energy plus final kinetic energy minus initial potential energy plus initial kinetic energy. Okay, final minus initial is the change in amount of energy. Thought the energy was supposed to be conserved. It is. It is conserved, but because we put in work, right? Remember, we were pushing up on the box with force FP. If this force FP were 0, then this would be equal to 0, and that would mean that the difference between these two things in parentheses here would have to be 0, meaning that the total amount of energy is conserved. And so there we have conservation of energy. If you like, we can always write FP times D as W for work. And there you go, conservation of energy from F equals ma. Now we'll move on to doing it with a little bit of calculus. All right, so with some calculus, we're still going to require that it be on a single axis. We don't need to have constant forces, but if we want to actually kind of evaluate something, we're going to need some kind of functional form for what the forces are, or we're not going to be able to evaluate anything. You're still going to have some caution as to what the positive and minus signs are doing. But again, as long as we stick with the definitions that we're doing, that acceleration is up, then we won't have any issues. Yeah, so kind of the same requirements as with algebra only, but not quite as much caution is necessary, I guess. Okay, so let's just go ahead and get started here. I assume then that you watched the algebra only one so that we don't have to go quite as slowly to go over these things. So we have the F equals ma is where we're starting. And we'll break up those forces into the pushing force and the gravitational force. And yeah, so remember then that the work is force times distance cosine of the angle between them. So the amount of distance that we move, though, remember, if we're going to do calculus, the amount of distance that we're going to move has to be a little bit of distance. And so distance is a little bit of distance. That means differential distance. So that means a little d to mean the little differential d, little differential bit, right? A little bit of distance. So this is small distance, which you should be at least somewhat familiar with having finished Calc 1, right? Okay, so that's the distance that we want to move, and so we will do the same thing that we did before and dot product it on in there to get energy showing up. Now, what are each one of these terms if we get things in terms of things that we can work with a little bit here? So Fp dot d, we'll do that one first. Just like previous case, those are both vectors pointing up. Since they're both pointing in the same direction and they're exactly parallel to each other, that means it's just going to be equal to Fp dd. On to the next one. Fg dot dd. Sometimes my d's look like a's. Hopefully the context clears up any potential confusion with that. So Fg, force of gravity, is mg dot dd. And they're in exactly opposite exactly opposite directions. So that means 180 degrees, therefore negative sign. Okay. Then we could do, now I just want to say, when we do the third case, there is another concept that will bring up, something called conservative vectors. We could technically talk about it here and utilize only things from Calculus 1 to be able to understand how that works in this context. However, I suspect that most people who have finished Calc 1 haven't encountered the concept of a conservative vector force, and I don't want to throw something completely new at you, having only required Calc 1. So that's why we're not going to cover that right now, but it could be something really cool. If you're going to take Calc 3 in the future at some point, keep that in mind as something that you may want to revisit this and have a look and see and really think about conservative vector forces and scalars. Okay. Okay. Then this third term, ma dot dd. Those are going to be in the same direction, right? We had previously defined that A is a vector pointing up, and we're sticking with that, okay? We're sticking with that A is being defined as going upward. Okay. And that's just because we know that we have to really fiddle about with positive and negative signs, and there's some stuff that we'll do just to kind of make our lives easier because of the limitations that we're setting to ourselves, working with only a little bit of calculus or a little bit of algebra or something like that. Okay, so that means we're going to have plus MAD D. And remember that this little d is attached to this d. It's not some separate variable. So there's really only 3 variables here, the m, the a, and the dd. There's not 4 separate things here. So just make sure that we're keeping that in mind. But we're going to want to have a look and see if we can break that up into anything else, much like we did on the previous one. So let's see. What is ADD? Is that something that we can do? Let's see. We know that acceleration is the change in velocity, right? As time changes. So that's going to be dv by dt. So if we have A times dd, that means that this is going to be dv by dt. If you're not going to get tired of me saying d over and over again, then I don't feel like I've done my job. So ADD is dv by dt times dd. And much like how we just kind of slid that difference in time over, we're going to just slide that dt on over to be underneath the dd and have this be dv times dd by dt. Well, this is change in position with respect to time. How much does that displacement change? How much has our position changed? How much distance have we covered? That's just our velocity, right? So that's going to be dv times v. I'm writing there in parentheses just so that it's clear what's happening. And since those are just multiplied by each other, we can multiply them in whatever order we want. V dv. So that's what we're going to stick with that. So we'll come back up here and write that this is equal to m, don't forget the m, v dv. Okay, so that's kind of cool, right? That we could go from mass times acceleration times this little bit of distance and get mass times velocity times a little bit of velocity, right? Whatever that means. Don't think too hard about what that might mean. It's mathematically useful for us, so that's why we do it. Okay, let's see. I think we're done with this bit, so we'll close that off. Now I'll just go ahead and substitute in those 3 results over here on our equation. We have fp dd plus, messed it up again, this should be minus, for the gravitational force, minus mg dd equals mv dv. mv dv. Now we want to integrate from the initial situation to the final situation. You know, a lot of times when you think about integration, especially the little bit that you might have done it in the beginning part of Calc 2 or maybe in Calc 1, is you think, I'm going to integrate along some axis. So that's going to be integrating from like x equals 0 to x equals 3 or something like that. Well, you can also integrate from a situation to another situation. And that means that if the integration variable, so like the x, the dx, if that integration variable might be d in one situation and v in another, well, I mean d in one term and then v in another, that's okay. You just look at your situations and pick out that specific d or that specific v. So let me show you what it is that I mean. What we'll do is we'll integrate from initial to final situation. And so for the initial situation, we're going to have, or see that we're going to have variables d and v. So that means the d, I, which we know is equal to 0, and df is just df. And we have some initial velocity and some final velocity. So what we do then is we write that this is going to be the integral of fp dd from 0 to df minus, okay, integral of mg dd 0 to df equals integral mv dv vi to vf. So you kind of see how we did that there, that it's really the situation that you're integrating from one point in time to some other point in time, and then all the values of the different variables that are associated with that specific point in time go on the bottom, and in the final point of time, they go on the top. So here's the bottom and there's the top. So doing up this integral, what we get is, if we assume constant forces, then the FP could come out of the integral. If we don't assume constant forces, well, we would need to know what some functional form of FP is, so that way we would be able to integrate it. But let's just assume constant forces for now. It's no different if you didn't have constant forces. Like I said, you just need to be able to find out what the antiderivative of it is. So we'll assume constant forces, and then the FP comes out, and then you just have the integral of just dd, which would just be df minus 0, so this would just be df then. And then this would be minus, the mg comes out, and again, df. On this side, the m can come out of the integral, right? And when the m comes out of the integral, we have the integral of v dv, right? Which let's do it step by step here. The integral of v dv from initial to final. What's that going to be? We know that. That's going to be 1/2 mv evaluated from, squared, from vi to vf. So that's going to be, let me write it a little bit more space here. So that means what we have is, kind of start writing it on this side a little bit, just so there's a little bit more room. Fp df minus mg df equals 1/2 mvf squared minus vi squared. This is just how much work was done. Just like before, this df is that final location minus the initial location. So that becomes mg times hf minus hi. And this is final kinetic energy minus initial kinetic energy. So that once again we have W equals our final potential plus our final kinetic minus initial potential plus initial kinetic energy. And once again we have conservation of energy now with a little bit of calculus in there. Okay, so the last one that we want to have a look at is if you've finished up some Calculus 3 class And so you now, at this point, you've talked about conservative vector fields. Talked about that. You've heard about that a little bit, maybe. We don't need to know too much about him. I promise. It's not too crazy. We are going to need to, so this is with, this is going to be through Calc 3. We will say that this is through Calc 3. We're going to have to require that our gravitational force is any conservative force. Really, it's not so much of a requirement as it is a leniency, right? It can be any conservative force. It doesn't have to be from gravity. But we can think of it as gravity. Gravity is a conservative force. Fp is non-conservative. So we have both in here then. We have conservative force and a non-conservative force. So we don't even have to really think of it as it's us pushing on it or it's gravity pulling it down anymore. It's just let your imagination run wild. Examples here, because sometimes when you're learning this in calculus class, they don't really give you examples of what any of this stuff means. So a conservative force is anything, you know, obviously I'm going to say this and someone's going to come up with a counterexample, but I always like to think of it as a conservative force is something that you can move either with, like you can move in the direction of that force, or you can move in the direction opposing that force. So this is can move with or against. So it's going to be things like gravity. It's going to be things like electric field. I know electric field is not a force, but it's also conservative because you can move with it or you can move against it. However, non-conservative would be things that you can only move against. Of course, you can come up with like mathematical examples where you can only move with it, but in terms of easily understood physical examples, a great example of a non-conservative force is friction. No matter which direction you're moving, friction is always opposing that motion, right? You can move this way and friction's pointing to the left, and if you decide, okay, I'm going to start moving to the left, then well, now friction's moving to the right, okay? So friction is a non-conservative force. But gravity is a conservative force because you can move up in opposition to gravity, or you can move down with gravity. So for any conservative force, we can always write it as the gradient of some scalar value, some scalar field. So that would be our conservative force here. It can be written as the gradient of some scalar field. So this is going to be a scalar function, also sometimes referred to as a potential or a potential function. Now maybe you can sense where I'm going with this. Due to convention, the potential energy is equal to negative of that scalar function. Therefore, the conservative force, so I might write this as having the little g on there. Therefore, the conservative force is equal to negative gradient of potential energy. Okay, and again, so the gradient comes from the fact that it's a conservative force. The negative comes from a convention. It's arbitrary, we don't need it there, but if you don't put it there, everyone's going to be really confused and not understand what it is you're doing because everyone else puts a negative sign there. So it's one of those things where maybe you don't like it, but you know, if you wanna play with everyone else, you gotta play by the rules. Okay, same rules that everyone else made up. That's how it goes. All right. So with that in mind, let's get started. We have the net force is equal to ma. Again, we're going to split that up. All right. Now we're going to dot product with a little bit of distance, just like we did on the previous derivation. Okay, so let's have a look at these one at a time here. If we do fp dot dd, we're actually gonna not change that one. Okay, we're actually gonna leave that one alone. So let's look at the second one first, fg, just because there's really not that much to do with this one. Okay, we're gonna let it be any conservative vector, and so it's not even necessarily up or down. You'll notice I didn't say we're restricting ourselves to one axis here. And so that means we can't really evaluate the dot product in the same way we did before, because we don't know what that angle is going to be, because we want this to apply to any situation. So without knowing what that vector, which direction those two vectors are going to be pointing, this is as good as we can do until we get to the step of integrating it, where we recognize that that's the definition of work. But there's other things that we can do though. So this would be dd, if we're doing the second one. So there's a couple ways to do this. Let's do it the naughty way first. So the naughty way would be that we just put in our definition for our conservative field, and we say that this is going to be negative grad u dot dt, and then we recognize that the gradient of u is kind of like a derivative with respect to distance, and this is multiplied by a bit of distance, so that the thing where you're left with is du, right? So that means we can kind of say and pretend that this is kind of like a du by dx situation, and this thing is kind of like a dx, so that those would cancel out, and all we would be left with is minus du. Now, technically, you're not supposed to do that. Technically, what we would need is the fundamental theorem of line integrals. What a name, huh? So, and by that theorem, that fundamental theorem, you wouldn't write this step and you would basically just get the answer. But this is a nice way to think about it. I think that this is a nice way to think about it to help make a little bit more sense, because that theorem on its own doesn't really tell us much. It's just going to end up showing us that once we pop the integral over here, we would have this, and then that's just going to be uf minus ui, all in just one line, you know. There's not really a lot there. There's not a whole lot of intuition to that, and so I really like presenting it this way, with the caveat that this is only a way to think about it sometimes, but this is what you should actually be doing, okay? So this is what's actually happening. This is just sort of a way to kind of help make a little bit more sense. Now let's do this third term on the right hand of the equal sign. So just like before, we'll change this acceleration into velocity. Notice we're keeping everything a vector this time. We're not getting rid of any vectors this time like we did previously. Again, we're going to move this dt over to hang out with the displacement. And then we're going to write it as v. So it looks an awful lot like what we had on the previous derivation, right? Let's try to remind ourselves what we had there. On the previous one, we had v times dv. Well, here we also have v times dv, but it's the dot product, right? So we have to actually do a little bit more work because it's the dot product. We can't just throw ourselves right in there and have a go at it. So let's look and see what we can do with this dv.v situation here. Remember that we can dot product in any order that we want, though. So we can do this as v dot dv. Now what we're going to try is a product rule. Okay, we're going to try product rule. And the way that I'm going to go about doing this is the following here. Just because I know sometimes it gets a little bit iffy. So what we're going to do is we're going to say that we have, I'm going to say, what does this equal? We're going to say that we have something that's v dot v, and we want the derivative with respect to time of this. Well, if we did that, it's just regular old product rule stuff, right? Derivative of the first thing, dv, dv, plus derivative of the second thing, right? Well, derivative of the first times the second plus the first times derivative of the second. Dot. These two terms are the same because we can dot product in any order. Okay. Now, if we, at this point, remove the dt from both sides, then what we end up with is d v dot v equals 2v dot dv. Which you notice is what we have here, right? We have v dot dv, and that's what we're wanting here. We just have this 2, so to solve it for v dot dv, and then we can get v dot dv is equal to 1/2 d of v dot v. And remember that any vector dot product with itself is just the magnitude squared. So this would be 1/2. Come on, there we go. 1/2 dv squared. V dot dv is this. Put a box around it. Okie doke. Therefore, our ma dot dd will be equal to m times dv dot v, which is this. So that will be 1/2 m d of v squared. So you see how we did that? I think no part of that is something that you can't do if you've finished Calc 3. If you've finished Calc 3, you can definitely do all of this stuff. It might be doing things maybe a little bit differently, maybe some things that you haven't seen before necessarily, like in that order or used in that way. But that's why it's really nice to really have a physics class that is applying the math that you're learning. But have a go and see if you can follow through that derivation there, okay? So let's now go ahead and plug in these things, this last one here, and this first one into our equation here. And we have this as FP, rotate my camera a bit, okay? FP dot dd minus du. And remember I said that technically we shouldn't be writing du here. Technically we should just be writing that whole thing right there and then use the fundamental theorem of line integrals. I'm going to keep doing it this way. And then this one will be 1/2 md of v squared. Throw the integrals in. And again, we're going to be integrating from the initial situation to the final situation. This one is just the definition of work. So this is just going to be W. Then we're going to get minus the final work minus the initial work. It's not work, sorry. The final potential energy minus the initial potential energy. And then this one's going to be 1/2 m. Now, although it's a v squared, remember that there's no other v over here, and there's certainly no v squareds. That means the variable that we're integrating with respect to is just v squared. So it's just like if we had a 1/2 m dx and asked you to integrate that, well, it would just be 1/2 mx, right? This one's just going to be 1/2 m v squared. For exactly the same reason. It's this thing that follows the d that tells you what that integration variable is. And that's going to be evaluated from I to f. So we kind of see where this is going, right? We kind of see where this is going by now. This is going towards W equals final potential energy, final kinetic energy, initial potential energy, initial kinetic energy. So see how you end up with exactly the same equation, no matter which of these three ways you go about deriving it. And all you need to do is start with F equals ma, and then think, how do we get energy out of F equals ma? Well, you just need to define work as the dot product of force times displacement, or force dot displacement. And that gets you conservation of energy in a mathematical sense. There would still be the experimental determination and all the history and all of that fancy stuff about what exactly it is that kinetic energy means, but the mathematics of it is pretty clear. F equals ma gets you conservation of energy.